Hello, everybody. So this is section 3.4, and the homework assignment is relatively short. I think it's about 15 problems, but it is on MyMathLab. And the main focus here are two things: rational zero theorem and something called Descartes' rule of signs. And they both help us understand a little bit more about polynomials. So the rational zero theorem is, well, actually, let me skip ahead a little bit. There are different types of numbers. There are real numbers and there are imaginary numbers. And now if it's real, if a polynomial has a real zero, then that number is an x-intercept. So all of these numbers are real. But there are two categories of real numbers. You're either rational or you're irrational. So rational numbers, you have an integer divided by an integer. So negative 19, that's just negative 19 divided by 1. That's an integer divided by an integer. 0 is 0 divided by 1. A third is 1 divided by 3, etc. So any number where it's an integer divided by an integer is a real number. I'm sorry, a rational number. Irrational numbers are the decimal go on forever and they don't repeat. But also, you cannot express these numbers as an integer divided by an integer. So famous examples are pi for sure, but any radical, any square root of a non-square. It's like the square root of 2, the square root of 3, but not the square root of 4, because the square root of 4 is just 2, which is an integer, which is rational. Those are all real numbers. And then you have imaginary numbers, 2i, or the square root of any negative number. So the rational zero theorem helps us narrow it down between for zeros that are rational. So polynomials have zeros one way or the other. Some of those zeros may be rational. Well, if they are rational, then the rational zero theorem can help us understand what they are. And so to apply this theorem, the theorem basically says if you take all the factors of the constant and then you divide those by all the factors of the leading coefficient, that will generate all possible rational zeros. So for example, here's a polynomial. You don't need to know it's the middle terms. You really just need to know this first term, which has a leading coefficient of 2, and the constant is 5. So I know that 3, there's no way that 3 is a zero of this polynomial, even without knowing these inner parts. I'm guaranteed to know that because of the rational zero theorem. How do I know that? Well, the factors of the constant, which is 5, the factors of 5 is prime, so it's just 1 and 5. Make sure to include positive and negative. And the factors of the leading coefficient, which is 2, is just positive 1 and 2. So I take all possible ratios of the constant to the leading coefficient. So 5 divided by 1, 5 divided by 2, 1 divided by 1, and 1 divided by 2. Always taking the constant divided by the leading coefficient. And I get a total of 8 possible rational zeros. This polynomial only has 5 zeros, 5 unique zeros at the most, because it's a degree 5. Now, if any of those zeros are rational, they must be one of these 8. Maybe all 5 of the zeros are rational. If that's the case, then all 5 of those zeros are in this group of 8. So let's apply it here. Here's another polynomial. It is a third degree polynomial, so I'm on the lookout for 3 zeros. I want to use the rational zero theorem to just list all possible rational zeros. Then I'm going to draw from that pool to use synthetic division to find a zero or a root. Once I find a zero using synthetic division, that third degree will become a second degree, and I'll use that to find the last 2 roots. So how do I find all possible rational zeros? Take the factors of the constant divided by the factors of the leading coefficient. So 2 just has factors of 1 and 2. 3 factors are 1 and 3. So I generate all possibilities. 1 divided by 1 is 1. So plus or minus 1 is a possible factor, possible zero, I mean. Plus or minus 1/3, so 1 divided by 3. Plus or minus 2, getting that from 2 divided by 1. And then plus or minus 2/3, 2 divided by 3. So step 1 is done. I've listed all possible rational zeros, and there are 8 of them. So I just try one randomly, and I chose 2/3 at first, so positive 2/3, using synthetic division. So I dropped down to 3. 2/3 times 3 is 2. 4 plus 2 is 6. 2/3 times 6 is 4. -5 plus 4 is 1, -1. 2/3 times -1 is -2/3, and right away, these do not add up to 0. They add up to -8/3. So that means 2/3 is not a 0. That means that this polynomial doesn't have an x-intercept at 2/3 comma 0. In fact, if I plug in 2/3 into here, I would get -8/3. That's the remainder theorem. So 2/3 is out, only 7 more to go. So let's try 2. I drop down to 3. 2 times 3 is 6. I add them up, I get 10. 2 times 10 is 20. -5 plus 20 is 15. 2 times 15 is 30. And this is a big no. That adds up to 28. So 2 is not a 0. 2 is a 28. If you plug in 2 into this function, you would get 28. That's the remainder theorem. So 2/3 doesn't work. 2 doesn't work. I've only got 6 more choices here. Let's try 1. If I drop down that 3, 1 times 3 is 3. 4 plus 3 is 7. 1 times 7 is 7. I add those up, I get 2. 1 times 2 is 2. -2 plus 2 is 0. This is a big breakthrough. 1 is a 0. And since 1 is real, it's also rational. But since it's real, it's an x-intercept. There's an x-intercept of 1 comma 0 of this polynomial. Also, the fact that 1 is a 0 means that x minus 1 is a factor. So if I were to divide this polynomial by x minus 1, I would get a remainder of 0. In fact, that's what I did here. But also, the result is a factor. 3x squared plus 7x plus 2 is also a factor. And the last 2 zeros of my polynomial are in this quadratic. You could do quadratic formula. You could go back to the drawing board and still pull from these numbers and apply them to this using synthetic division. But since this is a quadratic formula, I'd say it's just try to factor it. And if you can't factor it, quadratic formula, and then you'll be done. Quadratic formula tells you both the answers. This one happens to be factorable. And so my last 2 zeros are -1/3 and -2. So there are indeed 3 unique zeros. They are -2, -1/3, and +1. They're all real and they're all rational. So they were all in this list: -2, -1/3, and +1. Then there's something called Descartes' rule of signs. René Descartes, French philosopher and mathematician. He is the I think therefore I am guy and contributed a lot to philosophy and some mathematics. So this is a very fringe worthy kind of idea. So we know polynomials have zeros, right? Some of those zeros are positive and some are negative. But I'm only talking about real zeros here. Polynomials could have imaginary numbers, right? I'm talking about real numbers, the real zeros. And if a polynomial has a real zero, odds are it's either positive or it's negative. The only other option is it's actually the number 0 itself. So Descartes discovered a way to narrow down how many positive real zeros there are and how many negative real zeros there are. You look at the polynomial in the standard form and you count how many sign changes there were. How many times did you go from positive to negative or from negative to positive? How many times did that happen? The amount of sign changes tells you how many possible real zeros there are, or that number less by an even number. Let me show you what I mean. How many sign changes were there from 3x, from positive 3x to the third, all the way to -2? Well, from positive 3 to positive 4, that wasn't a sign change. But from positive 4 to -5, that was a sign change. From -5 to -2, that was not a sign change. So there is just exactly one sign change. That means there is one positive zero. This less by an even integer, well, I'll explain that. That'll make more sense in a little bit. Now, the amounts of negative real zeros, you take the function and you put in the opposite of x. So if I take this function and replace all the x's with their opposites, then this would become negative 3x to the third, because the negative sign wouldn't cancel out with a third degree. Still positive 4x squared, because the negative would cancel out, plus 5x, because -5 times -1x makes it positive 5x, and then -2. The 2 is the constant, which means constant. It doesn't change. So it's always going to be -2. Well, how many sign changes were here? From -3 to +4, that's a sign change. From +4 to +5, no. But from +5 to -2, that was a sign change. So there were 2 sign changes. That means there are 2 or 0 negative zeros. 2 or 0 negative. So there are 2 sign changes. So you would think, okay, 2 negative zeros. But that number or less by any even integer. So 2 sign changes, then you subtract 2, and that 0 is another possible amount of negative zeros. The reason why we didn't do it over here, because there's only one sign change. So if you subtract an even number from 1, like 1 minus 2, you get -1. And how could you possibly have a -1 amount of positive real zeros? You can't have a -1 amount of anything. One more example with these. Pause the video here and figure out how many possible positive real zeros are there with f of x. And then work out how many possible negative real zeros could there be. Hopefully you paused that video, and it's all about those sign changes. This one had 5 sign changes. So how many positive real zeros are there? Realize there are only 7 zeros in total. Some of those are positive, some may be negative, some may be imaginary. I don't know. But how many possible positive real are there? 5 sign changes means there are 5, 3, or 1 positive zeros. So 5 sign changes, but then less that by any even number. So 5 minus 2 is 3. So there could be 3 positive real zeros, but then 5 minus 4 is 1. So there could be 1 positive number. 5 minus 6 brings me -1, and I can't have a -1 amount of anything. But this does tell me good information. I know for sure there's at least 1 positive real zero here, at least 1. With the negatives, there were only 2 sign changes, so there are only 2 or 0 negative zeros. Remember, the whole thing has 7 zeros, so I could have 5 positives and 2 negatives. I could have 5 positives and 0 negatives, but that's only 5 zeros. What about the other 2? The other 2 would be imaginary. So I could have 5 positives, 0 negatives, and 2 imaginaries. I could have 3 positive zeros, 2 negative zeros, but then 2 imaginaries. 3 positive zeros, no negative zeros, but then I would need 4 imaginaries. So all these zeros are adding up to 7, the degree. This is assuming that none of these zeros are repeating. Okay, a little bit more about zeros. We know that zeros are connected to factors. If x plus 3 is a factor, then -3 is the zero, etc. But look at this. Look at these relationships. Rad2 and negative rad2. These two are conjugates of each other. If you change the sign, they are conjugates of each other. Notice -3 doesn't have +3 as a zero. But with irrational numbers, if the conjugates are included, then the coefficients will all be rational. And here are 2 imaginary numbers. These are also conjugates. You got a -5i and then positive 5i. So the negative and the positive, they cancel out when you multiply them. And if you have conjugates of imaginary numbers, then all your coefficients are real. So if you multiply, there are 6 factors here. If you multiply this all out, which would take at least 10 minutes, you get this big polynomial. And look at all these coefficients. They're all real. So that means the imaginary has a conjugate, and they're all rational. So the irrational part has a conjugate. That's going to come into play right here. Let's create a polynomial with real coefficients of a degree 4, and I have some clues. I have 2 clues. I know 2 of the zeros, 2i and 3i, and I know that if you plug in -1 into this function, you should get 200. Well, if 2i is a 0, that's a big deal. Then x minus 2i is a factor, right? And if 3i is a 0, then x minus 3i is a factor. Now, that's only 2 factors. If I multiply these 2 things together, I'm only going to get a quadratic, which is a 2nd degree polynomial, and I need a 4th degree. The key here is that real coefficients. Since I have real coefficients, any imaginary number I have has to have its conjugate to cancel out. So since 2i is is 0, I know that -2i is also a 0, which means x plus 2i is a factor. And since 3i is a 0, I know that -3i must be a 0, which means x plus 3i is a factor. This only applies when the coefficients are real, which happens very, very often. If the coefficients aren't real, you'll have a polynomial like 2x to the 6th plus 11i x to the 5th plus 4i x to the 4th. So your coefficients would be imaginary. But if all your coefficients are real, then the complex, the imaginary parts, cancel out by conjugates. So now I know, now I have 4 factors, and I can stop really looking, because when I multiply these 4 factors out, I'm going to get a degree 4. So now it's a matter of carefully multiplying. So I'm double distributing this first set, the second set. If you're really sharp here, you're recognizing that this is the result of a difference of squares. So when you multiply it, you're just going to get a difference of squares. Now here, this is a sum of squares, but you could think of it as x squared minus 4i squared, but then I squared equals -1. So -4 times -1 makes it the positive 4. And then multiply this, and I get x to the 4th plus 13, x to the 2nd plus 36. Okay, it's a 4th degree polynomial. I know that 2i and 3i are zeros of this because I used those numbers to construct this. The final test, if I plug in -1, will I get 200? Let's see. If I plug in -1, I get 50. So I'm not done yet. What can I do? You can't add 150 to this. Why not? If you add 150 to this, you will definitely make f of -1 equal 200, but that will change all your zeros. That will essentially, remember your transformations. If you add 150, you will take this polynomial and just raise it up 150 units, which means these zeros would change as well. So 2i and 3i would not be zeros anymore. The only thing you can do is multiply or divide by something, because multiplying or dividing won't change a 0. If 2i makes this whole thing 0, then I can multiply this whole thing by 8, and it'll still equal 0 when I plug in 2i, because 8 times 0 is just 0. So the bottom line is, I can multiply this by anything I want or divide it by anything I want except 0. And I will still have these zeros of 2i and 3i. So since -1 produced 50, I need -1 to produce 200. So I'm just going to multiply everything by 4. Now it becomes 4x to the 4th plus 52 x to the second plus 144. And plugging in -1 does result in 200. So now I'm feeling real good. That's definitely the polynomial. So fourth degree, the zeros are 2i and 3i plus their conjugates. And if you plug in -1, you're going to get 200. Last one, similar question. I've created a polynomial. This time it's a degree 3, and I'm given 2 zeros, and f of 2 is 522. Well, just like before, if 5i is a 0, then x minus 5i is a factor. But since the coefficients are real, 5i has to cancel out with its conjugate, which is -5i, which makes that new factor x plus 5i. Now, -7 is a 0, which means x plus 7 is a 0, is a factor. And there's nothing under here because -7 is a real and rational number. So I don't need a conjugate of -7 to cancel out. In fact, if I did introduce a conjugate, do you see the problem? I would have 4 zeros, making it a degree 4, but it's supposed to be a degree 3. So my imaginary pairing, my conjugates here, account for 2 zeros, and this -7 is the third zero. Now I multiply all my factors, and I'm going to skip a step here because realizing that this is a difference of squares, it's going to multiply to x squared minus 25i squared, but I squared being -1 makes that -25 positive 25. And then multiply again. I've got no like terms. So that is my first try, but I realize that f of 2 is 522. So I'm going to let x equal 2. And what do I get? When x is 2, I get 261. I need 522. So 261 is not 522, but 261 is exactly half of 522. So I'm just going to multiply this whole polynomial by 2. And that it'll become 2x to the third plus 14x to the second plus 50x plus 350. That's our final answer, but just to be extra careful, I'm going to plug in 2 and see if I do get 522. I think I needed to get, and I got it. And that is our final answer. So you have homework to do. You've got a long weekend ahead of you. Please take advantage of that and do the homework. We'll see you again on Tuesday.